Okay, everybody. So integrate this function over the entire plane R2. So this function will actually come up if you're doing any sort of probability or statistics. In other words, if you're doing any sort of quantum physics or chemistry, this will come up because probability comes up. Okay, so we're going to learn how to integrate this. The key here is switch to polar. So you won't be able to find an antiderivative for this function in x or in y, though you can try, but switching to polar will actually work. So let's remember what this means. It means that we have the r theta plane, and we're going to map it over by some map to the xy plane. And then our original problem was to integrate this function. Well, let's switch to formulas. It sent x and y to the number e to the minus x squared minus y squared. And our polar coordinates is the map that sends r theta to r cos theta, r sine theta. So remember, like, a certain point here has some r value, the length of this hypotenuse, and some theta value, which is the angle there. And so if we want to get the entire plane, then actually what we'll need is to integrate over theta goes from 0 to 2 pi to rotate around, and then r goes from 0 out to infinity. So it ends up that we'll want this rectangle that sort of just goes out forever. This rectangle is r goes from 0 to infinity, and theta goes from 0 to 2 pi. So this is A. Okay. And so, this infinite rectangle will go to the entire xy plane under the map G. All right, so the great thing is we don't have to deal with this function. We will integrate over this rectangle an easier function. That is the whole point of polar coordinates, is that this becomes e to the minus r squared cos squared, r cos, minus, and then y becomes r squared, or y becomes r sine, and so y squared becomes r squared sine squared. But then I just factor out a minus r squared, and what remains is a cos squared plus a sine squared. Notice how the minus was pulled out and became a plus. But that's 1. Turns out this will be an easier function. This is the function f after g. Okay. And so what we're going to see is that the integral, this integral here, which is the integral over the entire xy plane of the function f, will be much easier as an integral here, where we're integrating this function over this rectangle. So integral over a of f after g. But we have to correct for the volume. So the volume, we multiply by the volume correction factor, or the change in volume factor. Okay? And this are equal. Okay? So wonderful. Now we just need to figure out this volume correction factor then. Right? And it comes from the derivative, or the columns of the Jacobian of our parameterization map right here. So how do we get this? Let's go to formulas. So remember, this is the square root of the determinant of the Gram matrix of, okay, now how many columns of the Jacobian? Well, there are 2 input variables. So we'll have partial r giving W1 and partial theta giving W2. So we're really just going to have the 2 columns of the Jacobian, and let's compute them. W1 basically comes from partial r. Of course, writing equals, this is ridiculous, but you'll see what I mean is that I just take partial r of these, and I get cos sine. W2, the second column of the Jacobian, comes from the second input variable, theta. And I take partial theta of these. Cos becomes a minus sign. And a sine becomes a cos. Great. Okay, so I just need to compute the Gram matrix of these two vectors, take its determinant, and then take the square root. And that becomes a function of r and theta that I integrate. Well, multiplied by my other function. So we can do that. We know how to do dot products. Here we get cos squared plus sine squared. And that is 1. Now I take the dot product here, and I get minus r sine cos plus r sine cos. Check this. You get 0 when you take the dot product here. These are orthogonal vectors for any r and any theta. Last one. Well, why is that the last one? Well, because this one is always equal to this one. And what's W2 dot W2? So I take the sum of squares here, this product or dot product with itself. I get a plus r squared sine squared, and then plus a r squared cos squared. Well, that's great because I can pull out the r squared, leaving an s squared plus c squared, which is 1, so I get r squared. Here's my Gram matrix. I take its determinant, and then I take the square root. Okay, the determinant of this matrix is 1 times r squared minus 0 times 0. Okay, this is the change in volume factor. So that's what goes there. Excellent. This is the composed function. That's what goes there. And A is this rectangle, and that will sort of go there. I mean, we're just going to compute in, remember, iterated integrals over a rectangle are very easy. So let's do that. What do I get now? Well, let's see. Where does r? I can do rectangles in any order. So my r and my theta. Let's do r equals 0 to r equals infinity. Theta equals 0 to theta equals 2 pi. And then my function, composed function, is e to the minus r squared. And the volume correction factor was r. I could put it here, but let's put it in front over there. Okay, so I'm multiplying. This is a multiplication. Okay, so now I have this integral. All right. When I compute this, we're done. So let's compute this integral. Okay, so first, from theta equals 0 to theta equals 2 pi. By the way, you could do it the other order as well, but this is the function sending theta to r e to the minus r squared. Okay, so this function literally ignores theta. Theta does not appear at all. So if this is little h, then capital H of theta is just theta times that thing. Right? Take the derivative of this with respect to theta, and you just get a constant. Okay. Great, so h of 2 pi minus h of 0 by the fundamental theorem of calculus. And h of 2 pi is just 2 pi. I plug in a 2 pi for theta, and the rest stays. Minus h of 0, I plug in a 0 for theta, and the rest stays. Well, that's 0 times something is 0. So my answer is 2 pi r e to the minus r squared. Great, so now I'm ready to integrate over r. I have integrated away any thetas. Okay, so thetas are gone. Of course, they weren't there in the first place. But let's do r equals 0 to r equals infinity. We'll worry about this in a moment. What function? Well, it has to be a function of r, of a single variable. Okay, and now, okay, I called it little h before. I'm going to call this little h again, just because I don't want to invent a new number, and I need to find what's capital H of r. So this is where maybe I'll put in words that I experiment, which is another word for guess and check. Okay, so, I mean, maybe I just better take the derivative of this thing, e to the minus r squared. Single variable calculus. The derivative with respect to r of e to the minus r squared. Let's just see what that is. Well, e to the thing just remains. But then I take the derivative of the inside function by the chain rule. This is single variable calculus minus 2r. And then I look and I say, whoa, this is that. That is great. In fact, there's even a 2 there, and there's a 2 there. The only thing I'm missing here is a pi. I really wanted there to be a pi. And then I would know that this was my answer. This is my capital H. So let's mess with it some more. Let's take partial r of pi times e to the minus r squared. Well, pi is just a constant, so it hangs out. And I just get minus 2 pi r e to the minus r squared. Just exactly like I did before, except there's a pi. And now I'm saying, wow, this and this are almost the same. They only differ by a minus sign. And so actually, the final answer will be a minus pi e to the minus r squared. If this is my capital H, then its derivative is correct. And so, found it. Capital H of r should be this thing. Why? Because its derivative is the thing we are integrating. We have found the antiderivative. This is the antiderivative of little h. Great, so then the fundamental theorem says that I can plug in at the endpoints. Now, of course, my endpoints here are infinity and 0. Okay, so in Math 200, you will learn about limits and sequences and series in more detail. And we'll see that to plug in infinity really doesn't make sense, but rather to take a limit of some variable as that variable goes to infinity will make sense. But for now, what we should say is that we're just going to plug into this function. So minus pi e to the minus infinity squared, okay, and that's plugging in h of infinity, and then minus h of 0. So I plug in r equals 0, and I get minus pi e to the, well, minus 0 squared is just 0, which e to the 0 is 1, and so I just get a minus pi here. Minus pi is a plus pi. And then what I see is that e to the minus infinity squared is like 1 over e to the infinity. This is very small. And so as infinity gets more and more big, this will become, 1 over a big number is very small, and in fact it will go to 0. And so actually this whole piece here is a 0. And then I get minus pi. 0 minus pi is pi. So my answer is pi. This piece becomes 0. All right, and that's it. So let's look at what we did. We switched to polar. And then we found the volume correction factor and the composed function and integrated over a rectangle. We did the fundamental theorem of calculus once and then twice, and that gave us the answer.